Yeah, thanks. Actually, the two introductory lectures were interesting. I'll keep to the spirit of them in the sense of introducing things from first principles. In topic modeling, from first principles means where I was 6 months ago, which I didn't know much topic modeling at all. So I'll try to make it self-contained. But I'm going to start with something which is a little more, in a sense, basic or self-contained for the first bit, and then go on to topic modeling. So here's a simple setting. I want us to think about this because it's going to illustrate sort of the big thing that we are doing, which is really a small thing, which is thresholding. So the setting is this. You have a matrix A, which is n by n. There's a subset of k elements, call it S, and the picture looks like all the entries are independent random variables, but I've written out the picture here, and I'll say that in symbols there. For this is S cross S. This is a k by k submatrix, right? On that submatrix, the random variables, the entries are high. Mu is positive. Entries are high, so they are at least mu with probability at least half. Think of that as a signal. So S and mu, whatever that stuff is, think of that as a signal. In the rest of the matrix, the entries are normal 0 sigma squared. Think of sigma as the noise, and that is a signal, right? The idea is, of course, you want to figure out the signal from the noise, and you're not told much except you are given the matrix A. And here we might as well assume in this toy setup that we are given also mu and sigma. We don't have to be given them. And the big thing is to find S. Okay, S is your signal part. And those of you who are familiar with the planted-clique problem, you recognize this sort of planted-clique is a version of that, if you will, where you put ones there and plus or minus ones here with equal probability. Right? But they're all independent random variables. How would we do that? So let's call it obvious. Okay, so sorry, let me go back. If mu is much, much larger than sigma, you can convince yourself it's very easy to tell. If mu is much larger than sigma, let's say root log n larger, there'll be telltale signs of the big entries. The small entries, the tail is so small, they wouldn't encroach on the big domain, right? Again, let's not work out the details, but if mu is very big compared to sigma, you're home. Let's call this the signal-to-noise ratio. As it increases, your life becomes easier. In the planted-clique problem, if you will, mu and sigma are 1, so signal-to-noise ratio is 1. And we know that we can do the planted-clique problem at least if the signal-to-noise ratio there is root n over k, at least. That's just the same as saying 1 is greater than root n over k, or k is greater than root n. I've just written it in a devious way. Then we can find S. And now we actually know recently that we cannot beat this lower bound with statistical learning algorithms. I won't define what statistical learning algorithms are. The one thesis is that almost every algorithm we know is a statistical learning algorithm, and such algorithms cannot beat this, cannot do planted-clique. So here's what I'm going to do, not for the planted-clique, for the mu and sigma. I'm going to introduce, I call it a brave new step, half in jest, of course, neither brave nor new. You just threshold entries of A at mu. So you make them 1 if it's greater than mu, make them 0 if it's less than mu. This is a rather trivial and simple statement. We'll see that it buys us something. So what happened now? The entries in the k by k part are in expected value at least half, because with at least half probability you are greater than mu. The entries in this part, it's normal with mean 0 sigma squared, right? So the probability that they'll exceed mu is just this Gaussian tail bound. It's not accurate. I have a few other terms, but it's at most this much. That's it. Okay. So what good is that? Now we know B. We're not given E of B, right? We know B. So we just subtract this bit from every entry of B. So the mean is 0. And now what happens? See, this is something simple and nice happens. In this part, it's easy to convince yourself the spectral norm is at least k over 4. Just put the vector of 1 over root case, 1 over root case. Okay. By the way, this example is so simple that I'm running through the proof. In general, I may not do that throughout. But in this part, the entries are mean 0, standard deviation whatever, standard deviation exponentially small. So random matrix theory tells you the spectral norm is bounded by this. Okay. The only interesting thing about this is root n times an exponential factor, right? And therefore, if I now did SVD is the way we solve planted clique quite often. Now, if I threshold the matrix and then do SVD, I find that I'll succeed provided that k over 4 is greater than this, and that's just this, right? What has that bought you? Well, it's actually bought you something. Normal SVD would only win if the signal to noise ratio is root n over k, and now instead we only need an exponential in the signal to noise ratio squared, in fact, to be at least root n over k, right? So we get what seems like a big advantage, indeed it is, over what we can do with just SVD. So the moral of this story is thresholding, even if it's simple, can be quite nice and useful. Okay. And I want to point out one more feature of thresholding that's useful, and these are the two features. Actually, in fact, the second one is what we are going to use in this setup more than the first one. So suppose you have a bunch of data points. By the way, we'll not yet move to topic modeling. In a few minutes, I'll move to topic modeling, and then I'll tell you more or less from first principles what it is. So we have a bunch of data points in d-dimensional space. There are d features, if you will. Each data point is a vector in d-dimensional space. And let's think of the problem as follows. The data points actually come from clusters, like you have in a mixture model, if you will, except now the clusters are soft. What that means is that data point j has a weight wj belonging to cluster 1, and the rest of it belongs to cluster 2. So it might be half-half in the two clusters, or 3/4, 1/4, or whatever, right? More generally, there can be k clusters. Now, here's an additional feature I want to introduce. Now, this makes natural sense in this general setting, but it'll make much more sense in topic modeling. I want to say that each cluster has some dominant features, important features for that cluster. And furthermore, each data point has a dominant cluster. So the weights will not be half-half. The weights will be 3/4, 1/4, something like that, or 0.6, 0.4. One cluster will be significantly bigger in weight than the other for each data point. And we'll see that these make actually natural sense for topic modeling. Right now, they're just abstract things. And let's say that the dominance plays its role this way. Aij is greater than mu if feature I is a dominant feature of the topic, which is dominant in the data point j, and otherwise it's low. So this is high-low feature, just as you had in the problem I showed you with signal and noise. So signal, and this is noise, if you will. Okay. Now, I want to illustrate a second feature of thresholding now. If the heavy parts can stretch from mu upwards all the way to 1, the light parts stretch from sigma down to 0, if the variance above mu can be much larger than the gap between mu and sigma, right? So mu might be 0.4, you might go all the way from 0.4 to 1, whereas sigma might be 0.3. So the gap between 0.4 and 0.3 is smaller than the variance above mu, perhaps. Okay. Then if you just use two means, if you use any of your clustering criteria, you'll fail. It'll split the high weight cluster because it's very high spread, right? Very high variance compared to the low weight cluster. So normal clustering won't work, but lo and behold, thresholding will. So if I threshold at mu, I didn't say that, but if I threshold at mu, then the variance is taken care of, because everybody above mu becomes 1. And the variance is 0, right? If I knew mu and I thresholded at mu. So thresholding would really help in this case when the dominant things have very high variance, which is also going to be natural in the case of topic modeling. So that's all I'm going to say about thresholding. As I said, it's a simple idea, and that's going to buy us a lot. Okay, so here's topic modeling. This is, well, this first is just a definition of topic modeling, but the work I'm going to talk about is joint work with Bansal and Bhattacharya. So there are D features. Again, I'm going to assume only as much knowledge in topic modeling as I had 6 months ago, which is almost nothing. So I'll introduce it from first principles. There are D features. For some of you who know it will be boring, but there are D features which are words in the dictionary, 20,000, 30,000 words. A document is a D vector. A document just could be the frequency of words. This word occurs so many times, this word occurs so many times, and so on. No context, right? But it's just a D vector for us, right? And there are K topics. K is much smaller than D. So 20,000 words perhaps, but 50 topics perhaps. Okay? We have a collection of documents which cover 50 topics perhaps. And the Lth topic is also D vector for us. And the D vector just gives you the probabilities of words in the topic. Okay? So documents as well as topics are vectors, D vectors. And to generate a document, you generate a random convex combination of topic vectors. This is soft clustering. So each topic is a cluster, as I'll come to a little bit later. And you generate a random convex combination of the topic vectors, and then you generate words in the document in IID trials. Well, I didn't draw this picture, but I drew another picture, which hopefully will illustrate. Yeah. So generate words of document J in IID trials, and they are from multinomial with those probabilities. So that's the convex combination. Yeah, so you can imagine the picture. The topic modeling problem, which it's a standard problem, but I'm putting a twist on it that is worth paying attention. Given only this matrix A, which is a set of documents. Did I say what A was? Okay, I didn't say that. Sorry, excuse me. A is a matrix consisting of columns which are documents. I give you a bunch of documents generated this way. Okay, and I want to find an approximation to the K topic vectors. Okay, and I want the approximation to be good in L1 error. L1 error is natural for probability vectors, right? But the other thing about L1 error that's nice to remember is I have 20,000 long vector, right? If every entry is 1 over 20,000, it can be, it's a probability vector. If you allow L2 error, then I can just return 0 as a vector because the squaring takes care of it. So L1 doesn't have that property, so it's a bit more difficult. It's generally NP hard. Various versions, restrictions are all NP hard. But if this is not familiar, I really want to just make the point that it's just soft clustering. Topic vectors are cluster centers. Each data point, each document belongs to a weighted combination of clusters. So it's generated from a distribution, which in this case multinomial, doesn't have to be, with expectation equals the weighted combination of the cluster centers. Now, again, I'm going to show you a picture in the next slide. Maybe that'll make it clearer. So even if we manage to solve the clustering problem somehow, it's not clear what the clustering problem is. There aren't well-defined clusters. It's just soft clustering that we have, right? Even if you decide solve it, it's not clear. Cluster centers won't be document vectors, topic vectors, sorry. So that's a distinction from learning mixtures, which is hard clustering. So this picture, I hope this slide, we'll spend some time on it, will illustrate a lot of what I said. So ignore that for a minute. The mu's or topic vectors, in this case there are 3 topics. They are the corners of the simplex. Okay. Each x corresponds to one document. To generate a document, I generate a convex combination of the corners. So somebody inside the triangle, right? The red points, the red crosses, each correspond to one document. They are inside the triangle. But I don't give you the red crosses. Life would be very simple if I gave you the red crosses, right? What I'll only give you is the circles. They should all be black. Don't worry about the color of the circle. The circles are words in the document. So each circle corresponds to one word in the document, which is generated with expectation equal to the cross, right? But we are not given the crosses. So some of these words can be outside the triangle, remember, because the red things are inside the triangle, the weighted combinations of the topic vectors. But the circles, words which are generated with mean equals x need not be inside the triangle. They can be outside the triangle. Okay. Now, given what we are given is these circles then, no crosses, circles, and we have to find the mu's, the corners. Clearly, as you can see from this picture, it would really help us to find what are called nearly pure documents. A pure document is on only one topic. So if I have a cross sitting at a corner, that'd be really pure document. That's a document just on sports or just on politics and so on and so forth, right? I'm not given those, but if I could find the crosses at least close to the corners, every corner has a cross close to it. If I could isolate those, then I can hope that that's a good approximation to this. Even that is not true because this is a convex combination, so there's a bunch of those things, but at least I can hope that. So the aim of this, the first part of the talk, or much of the talk is to find these points near the corners, the red crosses. Okay. Let me do a little survey. This is a huge topic with a lot of nice literature, but let me just do a survey of few things that are very relevant to this talk. Early on, under assuming pure topics, that's assuming that each document is purely on one topic. Okay? So the crosses are right in the corners, but not the circles. Circles need not be in the corners. Right? So then, and assuming, making another assumption about primary words, that's 1 minus epsilon of the words are primary, you can think of primary words as sort of dominant features. Right? SVD solves this problem that was shown early on by Papadimitriou, Raghavan, Tamaki, and Vempala. Then the long-standing question was, can SVD, perhaps SVD cannot do non-pure topics. Non-pure means the crosses are not at the corners. They are anywhere in the triangle. In a way, well, I should say, the most popular non-pure model, which is really used widely, is Blinding and Jordan's model called latent Dirichlet allocation, which I won't spell out. But here, it's non-pure. Multiple topics are allowed. Topic weights are essentially uncorrelated, and there are various more difficult models, for instance, Bly and Lafferty. The trouble is, in this model, computation is difficult. The model fitting problem is probably NP hard, right? So, however, in a very nice paper, Anand Kumar, Foster, Xu, Kakaday, and Liu, in a sense answered this by showing perhaps not SVD, but if you use tensors, which are higher order correlations, you can view SVD as second order, then at least to L2 error, you can solve the problem in the LDA model. Then there's another paper of Aroraga and Moitra who sort of made some other assumptions. You have to make assumptions because these are NP hard. Assume that there are what are called anchor words and some other parameters. And anchor word is the following. They assume that each topic has one word occurring only in the topic and occurs with very high frequency. So the word is a telltale sign of that topic. So perhaps for baseball as a topic, the word run is an anchor word. Then you'll assume that it occurs only in the topic, which is a little strong, but it's possible. But you also have to assume that it occurs with frequency, let's say 0.02. So every 50th word is that particular word. And then they were able to give actually a provable algorithm at the end of it. Now the error, unfortunately, is still L1 error per word. So for a topic vector, the error is quite high. But it's a first provable algorithm and very, very good experimental result. Now that leads into our talk. Our aim here is first to spend some, since this is theory to practice, it's not all theory, but first intuitive and empirically justified assumptions. We'll have assumptions that we verify. And then we'll give a natural algorithm. I won't tell you the proof. The algorithm is natural and simple. The proof is actually quite a bit of work, but I'll indicate what goes on.
You'll tell us what are the primary words, whatever you...
Yes, I'll tell you all that. I'll tell you the essentials, right. No, I will tell you the essentials, yeah. Good, I mean, yeah. Sanity check. Okay, intuitive to topic modeling, not numerical parameters like others. Other things have to assume sometimes numerical parameters. Okay, so here are, so I won't use primary words. I'm going to use instead this assumption, which is a little bit different. Catchwords. Think of this as dominant features. So the assumption here is each topic has a set of words, not one word, but a set of words, each of which occurs more frequently in the topic than others. So we're not saying that it doesn't occur at all in the other ones, but more frequently. And together they have high frequency. So it doesn't have to be that one word occurs every 20th time in the document, but a combination of words, right? So that is catchwords, dominant features in other words. Dominant topics. Each document has one topic which is dominant, has a weight which is greater than a certain alpha, and every other weight is at most a beta, which is less than alpha. Okay?
Is there a bound on the number of catchwords allowed?
No, we don't need a bound. It can be enormous, but they're disjoint sets of catchwords. And their total frequency must be high, though. Okay, so a dominant topic. This seems a bit strong, that each document has a dominant topic. I'll show you empirical results that say many documents do, majority do. An open problem is to relax the each there, or throw it out, or say many. Okay. Nearly pure documents. We also assume that each topic has a small fraction of documents which are 1 minus delta pure. So there are a small fraction near the corners of the simplex, right? We assume that. And again, if you find those, you're done. And the fourth assumption we call no local min. That is, for every word, you plot the number of occurrences, number of documents in which the word occurs versus the number of occurrences. And that has no local min. That curve doesn't come down and stay down. And the justification for this is these plots often tend to be Zipf's law, which is power law, but power law doesn't have a local min, it declines. But for catchwords, it's not going to decline in the beginning, it's going to increase and then go down. But it's still unimodal, and it applies in these two cases. In fact, empirically we observe that these are the two things that happen. Now, well, I don't think you need to remember all these four, but hopefully you got the gist of it. The first one says dominant features, the second one says dominant topics, dominant clusters in other words. Okay. The third one says points near the simplex corners. The fourth one is perhaps a little technical, but it's based on these two possibilities.
How does it relate to the Aurora moisture model?
Okay, so their assumption of anchor words is stronger than catchwords, much stronger than catchwords. They don't assume dominant topics, and they don't assume this, but their dependence on various numerical parameters are there, plus the error is not L1. So I think the crucial thing is the error is not L1. So if you don't have the error L1, you can throw out small words. But we observed empirically that there are small words occupy constant fraction of the entire document. So there are words that only occur 5 times in the document, right? You can't throw them all out. If you can, then you get more freedom. But we don't throw them out. So the algorithm will be described. I'm going to describe the steps of the algorithm in one slide. For this talk, S is the number of documents, S sample, right, because it's being generated. For this talk, we assume the probability that each topic is dominant is 1 over k. It's not assumed in general. So, threshold step, much like in the signal to noise problem and the other one, I'm going to do a threshold. But here, nobody gives me mu. I have to find the threshold. Furthermore, the threshold is going to be different for different words, because word frequencies are different for different words. So, for each word I, the threshold is going to be the first gap as you come from above. You take the maximum zeta so that aij greater than zeta for 1 over 2k fraction of the j's. That's meant to be half of this. So you've captured an entire dominant topic. Half of a dominant topic. But then you look for a gap that is at zeta itself, there aren't too many, epsilon small. Okay? So you've covered at least half the topic, and then you go until you find the first gap. And the proof, I won't tell you the proof, but we can prove that you've cut off the entire topic exactly, more or less exactly. Okay. And then you use SVD on the thresholded matrix, so very crucial, just like the signal to noise problem. You don't apply SVD on the data matrix, you apply it on the thresholded matrix, and that gives you centers for a k-means run. Then you do k-means clustering, and at the end of this, we prove, again, I won't prove here, but it can be proved that this identifies the dominant topic. So for almost all documents, I've got correctly what the dominant topic is. Again, I'll show you a picture with the triangle in a minute. We're not done yet. Then we identify catchwords for each topic, which are the set of high frequency words in each cluster, and this we will have to prove that that is a set of catchwords. Once you've identified catchwords, you finally get to your aim of identifying things near the corners, pure documents. Those would be the set of documents with the highest total number of occurrences of catchwords. Okay? We'll show that they are nearly pure documents, and therefore their average will be close to the topic vector, because they are the ones near the corners. Okay, here's a picture. What the SVD and k-means and all that does is just identifies dominant topics. What does that mean? So I've drawn only the region where the top topic is dominant, things closest to that, if you will. I would have identified all the circles in this region, and also all the circles in this region, all the circles in this region. That's what the clustering will do. See, how many minutes was the talk overall anyway? No, you can tell me one of the two. When does it end?
20 minutes.
20 minutes, okay, yeah, good. Okay, so I think we are fine. This is what I've accomplished in all the way up to here, right? The clustering. Not the soft clustering. I mean, these things really belong quite a bit to this cluster too, right? But we've identified the dominant topic. So, are we done? Now, I claim we are far from done, because if I took the average of all the circles in this region, I would not get anything like the corner, which is what I'm aiming to get. I get somebody in the middle, right? That's of no use. So that's, of course, very different from hard clustering. Right? In hard clustering, there'll be spew around there, but that's not happening. There'll be a few points outside as well. Okay. So now I'm going to backtrack and tell you a few things about the proof. So thresholding, what does it accomplish? We saw what it accomplishes in the sort of signal to noise setup. Let's see what it accomplishes here. We'll prove that it turns out that thresholding, we can use the no local min assumption, and that implies thresholding does not split any dominant topic in the middle. So it doesn't split any of these clusters in the middle, thresholding. Would not be very nice if it did. Okay. So threshold matrix is a block matrix for catchwords. For non-catchwords, it still doesn't split a topic, but they can be high on several topics. Okay, yeah, so maybe it's not. This is nice because you have a board as well as, so you don't have to prepare your pictures in the beginning. So this is topic 1, topic 2, topic 3, topic 4. These are documents dominant in that. These are catchwords for topic 1, 2, 3, 4. And there are a lot of non-catchwords. And this is very important because empirically one observes that quite a lot of words are small number of occurrences. So if the thresholding is ideally correct, this would all be 1. This would be a diagonal matrix. And these words would be 1s on perhaps several topics and 0s on others. And so on. If the picture is ideal. Of course, it won't be, right? There will be a lot of fuss. By the way, in the paper, we don't set things about the threshold to 1. They are weighted as well, but right now we just pretend it's 1.
There is only one catchword per topic?
No, many catchwords. So this is, I'm sorry, so I drew it, this is really a number of words, sorry. Okay, so there are many rows in there. Yeah, many rows, all ones, if it's ideal. Yeah. So if it was ideal, then you'd be more or less done, you would think. I mean, somehow you should be, but it's not going to be, that's the problem.
By the way, on the previous, you showed this picture with the 3 simplex, and then you said things are not clustered, but this seemed like just a kind of very low-dimensional. This is a low-dimensional phenomenon, right? You were using the fact that.
No, we are still living in D dimensions, significantly so because.
No, but I mean in your picture, the fact that the simplex constraint forces, makes it so that these things.
Oh, I see. It's a k-dimensional simplex sitting in D space. So we are still up there in D space. We have not come to the K space.
Just the fact that it was in the picture it was a low-dimensional simplex, made it seem as though these topics are very far from from their dominant. These documents are very far from their dominant topic. But this was.
Oh, you have a good point. So the points are a little more pushed towards the corners. Yes, but so we only assume that the dominant topics are weight 0.4 or 0.3 or something. The 0.7 of the weight comes from the other topics. But hey, the floor is open also to non-organizers. If you have questions, you can. So, okay, so we have that. So that's after thresholding. We already have something like that, right? But of course, the picture is fuzzy, so you have to use clustering to do the job, right? Now, an important point in clustering is, which I said before, and thresholding helps this, but let's do a picture. So we might have a bunch of clusters. There are 2 parameters of interest. One is the inside cluster spread, and the other one is the spread between these 2. So this is A, this is B. So what we need for clustering intuitively is A must be bigger than B, right? Otherwise you'll confuse clusters. So let's see if that's true. So we need inter-cluster separation to be greater than intra-cluster spread, variance inside the cluster. Now, catchwords provide sufficient inter-cluster separation. So catchwords, so this 1, 0, and 0, 1 says these two clusters are very far apart, okay? Sufficiently far apart. So that satisfies one side of the inequality, that inter-cluster separation is large. How about intra-cluster spread, variance inside a cluster? So inside cluster variance, it turns out can be bounded, but this needs machinery. We have to use machinery from random matrix theory. And there's one little nice thing nowadays is that in random matrix theory originally, right, we knew things where all entries are IID independent or independent. At least now we know, of course, substantially equally good results, almost, when only the rows or only the columns are independent. So the documents are independent vectors. It's not true that words inside documents are independent, right? If a word occurs in a document, it's less likely that some other word will occur. So there's a lot of dependence there, but that's fine. Random matrix theory by now is just as good for that as it was for independent entries, so we can use that. Now, we also crucially use something else. So we use a result that I had a few years back, which says the following. If inter-cluster separation, this A, much greater than B, you don't need that. You only need that inter-cluster separation is much greater than inside cluster directional standard deviation. That means a standard deviation in one direction. And that actually is of general importance. So maybe I should draw that picture to tell you why that's important, why that's not trivial. So if I had two Gaussians of the same variance in d dimensions, right? Let's call it the center separated by delta. We all know that as long as delta is now, this is just two Gaussians here, a few standard deviations away. This is a result in general of Impala and Wang. For two Gaussians, it's completely trivial that sort of intuitively the mnemonic is if the inter-center separation is at least a few standard deviations, where the few does not depend on the ambient dimension d, right? D can be very large. Then you can separate them. You can cluster and separate them, right? And this is a generalization of that. You only have to take, what is it saying? You only have to take the standard deviation sigma in one direction. The overall spread of the cluster is root d sigma, right? Because there are d dimensions. So you cannot require that the centers be apart by root d sigma. That doesn't happen in reality. It's sufficient that they be apart by 1 sigma or a constant number of sigmas. Okay. So that's true in full generality, and that's a result from there. And using that, then you can separate that.
There's no dependence on K?
There's a dependence on K. Yeah. Well, I don't know the best. What is it, Santosh? What's the best dependence?
K to the 1/4.
K to the 1/4. Okay. Good. Now I can ask the audience questions as well. Yes, K to the 1/4 is the best separation, but yeah.
Is it chosen based on the catchwords? I mean, if you have a certain number of catchwords, you know how well defined the clusters are.
So in the setup so far, I'm assuming K is given to you by God, right? I mean, just you have to.
It's a core truth.
Sorry?
It's a truth.
Yeah, it's a truth. But you can play around with different Ks. I haven't, I'm not going to talk about that, but yes, indeed, that's an issue. How to choose K if you're not given it. Okay, it doesn't matter. Oh, this is the picture. I thought I had a picture. Okay, I am now going to the experimental slides, but I had oh no, I'd already showed you the two pictures I had. Okay, good. So that's so far the theory part. A little on the experiments. Nice to make it full, right? People don't all use Windows somehow. How do you make this full?
Top left.
Left.
Red,
Green. Okay, good. Okay, so I'm not an expert on the experiments, but we did do them. My co-authors did. So we're going to just
Try Apple L.
Control L.
Apple.
Apple L. Where is Apple?
Right where the Windows button should be.
But it's, it says command, right? No, that doesn't do that. Okay, now, Windows button, it should be, it's a function button there, okay. Not function L.
If you go view menu, under view, over there.
Oh, and,
Patient is
okay,
correct.
good, yeah. Oh, great, thank you. Thanks a lot. By the way, you can not only ask questions but change the slides as well. It's useful. So we did, I don't know, there were four corpora of documents. You know, they had so many documents and so on and so forth. Okay, so this is checking the assumption. So one of the things we did, I'll show you only a couple of these. I'm not going to show you all the other stuff. But the number, so why did we make these assumptions? Are they valid, right? So the fraction of documents satisfying the dominant topic assumption, alpha is saying that the topic weight should be at least 0.4, the dominant topic. If you want the dominant topic to have 0.8 at least, that's of course requiring a lot. There aren't so many. At 0.4 there are quite a few. I should backtrack one step. I should tell you that even in LDA we know, and it was folklore and now we have a simple proof that the prior puts a lot of weight on one topic if what's called the concentration parameter is low. And in fact, but these are empirically observed. So we take the corpus and then we look for, after we fit, the model will look for whether dominant topics exist. They exist in this percentage of documents with 0.4. As I said, it'll be nice to, I think the thing will work if the assumption is changed to only a constant fraction of the documents of dominant topics. We don't have that yet, we assume everyone now. Catchword's assumption, rho is the gap. That is, you are 1.1 times more likely to be, the word is more likely to occur 1.1 times by a factor of 1.1 in the dominant topic than other topics. And then you find that almost every topic has catchwords, okay? And this is the total frequency of catchwords in the topic is 0.05 and so on. So this says every 20th word is a catchword. This says every about 9th word is a catchword and so on in the topic, right?
Do you know here, do you need to use many catchwords in order to sort of satisfy?
Yeah, I think 20-ish. Number of catchwords is 20. Yeah. I mean, I don't know the answer to all the experimental questions, but that I remember, yeah, it's about 20.
I guess, did you compare to see if the anchor word assumption holds or not on these corpora?
So many topics don't have anchor words. Okay. Well, see, so I have to say it with a catch. So if you want a word that occurs in the topic mostly and not so much in other topics, they do exist. But if you want it to have a reasonably high frequency like 0.05, then it's a problem. If they're very low frequency, the theoretical bounds they give are very high. So, you know, so you don't get anchor words if you assume, let's say, 0.05 frequency is necessary. This is about how these things were done, right? So,
And the catchwords, how do they look like? Can you interpret them well?
yeah, actually, I didn't have that slide, or may have it somewhere, but they do turn out, they seem to be nice words. I mean, so, yeah. So in machine learning, I mean, we have a list of words that came up, but they seem to be decent words.
And if you compare it with other methods, how the interpretations they look like?
Coherence or... Yeah, so I have some of these more interesting nouns like perplexity and coherence and so on. Yeah, at the end. I don't know what they are, but they are coming up in the pictures of them. But they seem to be nice words in general. So how the methodology, this is similar to Areraga and Moitra, that is, we generate a semi-synthetic corpus from the LDA model. First you take a real corpus, then you train an LDA model on that using standard methods. Okay. That gives you topic vectors, and then you generate semi-synthetically from those topic vectors. That's what we did. So this is the procedure to do this. Oh, and we used what you could say is a lowish Dirichlet hyperparameter, if you're familiar with that, doesn't matter. Dominant topic assumption is not assumed to be satisfied, right? So for the theory, we made all these assumptions. We did not assume for the corpora we got, right? They don't have to satisfy the assumptions, but still you get decent results. Now decent means this. So the L1 reconstruction error on various semi-synthetic sites. So this, I think, this is our algorithm. Thick means I think it's better. So these two are our other gain-Moitra algorithms due to them. I think this is better. Their KL algorithm is generally better than their L2.
What is the difference between these two?
I think KL it's not really KL, but KL is used as a measure for how much the algorithm has converged. Both are similar. In both these cases, they identify anchor words, and
Only the convergence criteria.
only the convergence criteria is different. Let's see. So we do worse on the 20 news group by a little bit, but the others we seem to do better. That's the reading. Okay, so I should say the L1 error can go up to 2, right? Because the 2 probability vectors. So generally you get these kinds of L1 errors. That's I don't know whether those numbers are great or anything, but you get them at least. They seem to be good actually. Consider. Okay, this is the question you asked. Perplexity. Where is that what this is? No. This is also. I'm sorry. This is so. This is showing that in fact what happens with our algorithm, and we were puzzled for a while on this. That in fact on most topics we seem to have fairly low L1 error, even lower than what's reported, but we do get outliers. These have very high L1 error. So this x-axis is the L1 error, right? 1.2, for instance, right, on one topic. Greater than 1 is possible because there are 2 probability vectors. You can go up to 2. But there are 2 topics which are very bad. The rest seem to be good. So this is an illustration that happens. This is your perplexity, and somebody in the audience will know better the definition of these things. Perplexity is some estimate of the posterior probability in LDA, which is difficult to compute exactly.
It's e to the minus likely posterior.
E to the minus likelihood, right? But an approximation to that, because
Because
you can't do the exact thing. But that's introduced by Blyning and Jordan. That's used quite often for all of these things. Then, let's see if I have any more. That's all I have. Okay, I think I'm done. So just in time, you can ask questions if you want.
Can I ask something? Like, usually when we run LDA in practice, like the choice of K is a huge problem. Now, with all the theoretical assumptions, does it offer a way to guide the choice of K or constrain that?
Yeah, so that's a very good point. So I think we haven't done this yet, and I haven't proved anything, but I would suspect if you try a few Ks, the right K will stand out quite a bit. So I'm going out on a limb on this. I have neither theory nor experimental back, but I think that would be true. But indeed a good question to see how you can get at the right K.
So it seems one of the assumptions is the corner of the simplex has a lot higher probability of being hit. I guess I've seen data where, say, the 1D subspaces are high, or the 2D subspaces. Like you're going to have sports, and within sports you're going to have, baseball and soccer or whatever, right? So have you considered any kind of
hierarchical stuff, you mean, or something like that?
Well, just that in the case of, like a triangle, that there wasn't a lot of points in the corner, but there was a lot of points on the edges.
Oh, I see. It's not okay. So there is a vague intuitive argument that in fact you must assume that there are points in the corners for identifiability. So you cannot hope to get the exact corners with L1 error unless you have sufficiently many documents around there in some sense.
Suppose all the points are on the one simplex.
Because so if what is the problem? The overall problem is just to find a simplex that encloses all your data points more or less, right? But I could have found a very large simplex. That's not useful. Right? I must find, in a way, the smallest simplex that encloses your data points. Then smallest, what does it mean? Volume and so on and so forth, right? But if you assume enough points on any of the corners, you can say you must find a simplex which consists whose corners are more or less data points you have, and still enclose most of the data points. So that pins down identifiability. So you need something like that. I don't know how to do it if you had only points near the edges, where you have to find smallish simplex containing all of them.
I thought he was asking a different question, where instead of the topics being single points in space, the topics are, let's say, line segments, and your space is the convex hull of these. Can you then identify the line segments, because now they correspond?
But is that what you're asking?
Yeah, something like that.
Yeah. No, I don't know. I mean, but in topic modeling, usually you seem to assume that topics are single vectors. But yes, I mean, it's fair enough that you could try that. I don't know. No idea.
But if you do not want L1 error, right, like the comment you made about like you need points near the corners.
Right.
If you do not ask for L1 error, then you can.
That's true. If you don't ask for L1 error, you can live without points near the corners. So if you're allowed L2 error, right, then you can ignore small coordinates, and then you don't need points near the corners. You can do it without. So maybe that's true. So maybe L2 error you can do.
It seems like the definition of core words was implicit, and the core words get assigned to topic for some probability close to 1. So if you relax that assumption, then what happens to your ability to identify topics? In other words, you know a priori that certain core words are assigned to probability 1 minus epsilon to certain topics. And if you didn't have
Oh, you mean? But no, we don't assume 1 minus epsilon. That in the topic vector, catchwords might have very low frequency, but they should have even lower frequency in the less dominant topics. That's all we assume. So the frequency of a single word in a topic might be 0.001. It might still be a catchword because it's only 0.0005 in the other topics, right? But the list of catchwords together should have high enough frequency. And that seems realistic. In a sense, we do see that there are catchwords like that.
Can you assign it? You have to know which topics the catchwords belong to a priori?
No, we don't have to know anything like that in the beginning. So we find all that. We find the catchwords for each topic.
Well, I have a quick question. So have you actually compared to LDA itself, not to the model, but to the recovery?
Okay, so that's a good question. Here is actually a fundamental question. How do you compare to LDA? What is a measure of comparison? Perplexity is a possible measure, but it's not a precise measure. Okay, LDA, so you can say there's a real corpus. I find topic vectors using LDA, but we don't know that they are the right topic vectors, right? The only thing we would know if we could compute the posterior accurately, which is better. But I don't think we know how to compute the posterior well enough.
Well, one thing you could try, you can generate something from LDA model and then try to recover it back. That, of course, would be an unfair advantage to the...
No, that's what we do. LDA model. So,
but you don't. I think you don't compare. Maybe I'm mistaken. Do you actually compare to LDA inference?
That's what the perplexity is doing, right?
So
But,
perplexity is compared directly to...
it's like the e to the minus posterior, but the bound on posterior because
it's a relaxation of the posterior which you can compute.
But, well, maybe we can... Any other questions?
Thank you very much. Thank you.